Hello and welcome to the second lecture for ECE 1B for spring 2020. Before starting today's topic, I would like to remind you of a few items regarding the administration of the course and evaluation. Firstly, I want to remind you that after each lecture, after the scheduled date of each lecture, which is Monday, you have until Wednesday at 6:30 p.m. to submit answers to 4 questions that are embedded in the lecture slides. They're labeled Q1 through Q4. So you need to answer those questions in order to be considered present in this lecture. Now, of course, your answers should have reasonable quality. For example, if I ask you a question whose answer is just one number, it's not okay to just cite that number without any argument, derivation, proof, and so on. So you have to justify each answer. And you have to show that you have actually worked on the problem. Now, your answer does not need to be correct for you to get credit for presence. You have to show that you have considered the problem, spend a reasonable amount of time thinking about it, and you show your work in the submission. Now, each submission, as I've mentioned before, should have a specific subject line. You send it through email to me, and the subject line should read ECE 1B, spring 2020, and then the word attendance, and then the date. So the first lecture was 03/30, March 30th. This lecture will be 04/06, April 6th. So from the subject line of your email, I should know which lecture questions you're answering so that I can direct your email to the appropriate folder. And then at the very beginning of the text of your message, please include your name and perm number. The class has around 100 students now, and it's extremely difficult to locate you on the class roster for recording your presence if you don't provide name and perm number. Okay, another request that I have from you is those of you who don't have photos on Gaucho Space, please provide a photo. This is one of the few things that connects us to each other in this quarter where we don't have face-to-face meetings. I've included my own photo on Gaucho Space, and many of you already have photos. Those of you who don't, please do consider adding a photo so that we get at least this minimal acquaintance in terms of name and faces. In the first attendance evaluation, I was very generous to give you credit because it may not have been clear to you what I expected. But from now on, I do expect detailed answers with justifications in order to get credit for attendance. And if sufficient detail is not provided, I will reply to your email and ask you to provide the details. So I'll give you one chance to improve on your answers. If the second answer is still unsatisfactory, then you'll be marked absent. Okay, hope these points clarify the expectations. Now, today's lecture is entitled Placement and Routing, or Routing. The word is pronounced both ways, routing or routing. And we'll come to know what it means as we go through the lecture slides. Okay, so let's now start, as usual, with puzzles. So here's a simple puzzle. There are n houses on one side of a street and 2 utility companies on the other. We want to connect each utility facility to every house via lines of any desired shape such that the lines do not intersect. So in this example, I've shown 5 houses, but you can do it with 6 houses, 7 houses, any number. 2 utility companies, in this case, the water utility and electricity. And we want to connect each utility to each of the 5 houses by drawing lines, and those lines should not intersect. So please, before advancing the video to the next slide, try this on your own and see if you can solve this simple warm-up puzzle. Draw lines from the 2 utility symbols to each of the 5 houses. The lines should not intersect. Okay, here's my answer. You draw the water utility to the houses using straight lines. Then, of course, you cannot connect the electric utility to the houses using straight lines without intersecting. So you do something like this. This is to the first house. This is connection to the second, to the third, to the fifth, and to the fourth. Okay? So it is possible to draw lines from 2 utility companies to 5 houses so that those lines do not intersect. So the idea is one set of lines, the blue ones in this example, go straight from the utility to the houses, and the other set of lines, the red ones in this example, go around and connect to the houses from the other side. And you can do it with any number of houses. Okay, so now here's the main puzzle for today. This time I have 3 utility companies and 3 houses. And I want to do the same thing, connect each utility to each of the 3 houses so that the lines do not intersect. Again, before I start revealing my attempt solving this puzzle, please spend a couple of minutes at least experimenting with this, drawing lines, and see if you can solve the puzzle. Okay, so do not advance the video until you have worked on this puzzle for at least a couple of minutes. Okay, again, I draw straight lines from one of the utilities to the houses, no problem. And I connect the second utility from the other side, as I did before. Now it's turn for the third utility, the gas utility in this example. Okay, here is connection to the first house from the right. Here is connection to the third house. Now I'm stuck. There's no way to connect the gas utility to the middle house without intersecting some lines. So if I go straight, I would intersect that blue line. If I try to go around, I will intersect the red line on top of the house. Of course, this doesn't mean that the puzzle cannot be solved. It's just that this attempt didn't work. So one may spend some time drawing the lines in different ways to see if there is some solution to the puzzle. Well, this is actually a trick puzzle. The solution is impossible unless you're allowed to cut through a house. Okay, so if I'm allowed to cut through a house, I could do something like this. I could connect the gas company to the middle house. Oops, sorry. By going through this house, and then I won't be intersecting. Okay, so you see the point. I'm having a hard time drawing lines with my touchpad, and I can't use, unfortunately, a pen on this computer that I have. All right, so let me promise you at this point that I won't give you any such trick puzzles anymore during this course. All the puzzles that we'll deal with, except for this one, have legitimate solutions. This one doesn't have a solution. Of course, trying to solve the puzzle for 10 minutes, 15 minutes, an hour, and not coming up with a solution does not mean that the puzzle does not have a solution. It just means we did not succeed. However, we can prove actually that this puzzle is unsolvable. And I'll show you a proof in a few minutes. So this slide lists some history and variations on this puzzle that I'm going to let you read on your own. So in order to discuss why this puzzle does not have a solution, we're going to simplify the representation. Instead of drawing houses and utility companies, we simplify the representation to black dots representing houses, say, and white dots or white circles representing utilities. So the warm-up puzzle at the beginning is represented by this graph. Okay, the graph is basically a graph of 5 black dots or nodes or vertices in graph theory terminology, and 2 white dots. And those are the connections. The lines represent the connections that we try to make. Now, this particular graph is known as a bipartite, complete bipartite graph. Bipartite means the nodes can be divided into 2 parts, in this case the black nodes and the white nodes. And complete means every one of the white nodes is connected to every one of the black nodes and vice versa. Now the main puzzle that I told you is impossible to solve is this other graph on the right. 3 utilities, the white circles, or white disks, I should say, and 3 houses, the black disks. And again, every one of the white nodes is connected to everyone, is to be connected to everyone. So these graphs have names. K represents for complete graph, and the subscript 2n means that this is a bipartite graph, 2 parts. And the 2 parts have 2 nodes and n nodes, respectively. So 2 white nodes, for example, and n black nodes. The other graph is known as the complete bipartite graph 3-3, means each part has 3 nodes, 3 white nodes, 3 black nodes. And of course, the color of nodes is immaterial in the sense that in the first graph, I could have said 2 black nodes and 5 white nodes. It's basically the same graph. the color of the nodes has no significance except to distinguish them from each other. Okay, so the puzzle we are dealing with is represented by graphs of this kind. And the question whether we can connect utilities to the houses, or white nodes to black nodes, without the lines crossing each other is equivalent to asking whether these graphs are planar. A planar graph is a graph that can be drawn on a plane without its edges intersecting. Okay, we can draw it on a plane, two-dimensional plane, without the edges intersecting. So the puzzle is basically, the warm-up puzzle was, is the graph K2n, the bipartite graph with two nodes and n nodes, planar for any n? And the answer was yes, it is. The main puzzle, the classic puzzle, asks the question, is K33, is the complete bipartite graph with three nodes on each side, planar? And the answer I claim to be no, although I haven't proven it to you yet. Okay? So be patient, I'll show the proof. So these puzzles basically are asking whether specific graphs are planar. They can be drawn on a plane without their edges intersecting. I mentioned that it doesn't matter whether we have 2 black nodes and 5 white nodes or vice versa. So the complete bipartite graph Kn2 is really not different from K2n. In both cases, one part has 2 nodes and one part has n nodes. So this is a drawing of K33, a partial drawing, and we have to add, so a different way of drawing. So I'm trying to connect every white node to every black node. I've done all of them except for this one. And you see that this connection is impossible. If I go straight through inside the circle, it will intersect a line. If I go around and try to connect from the other side, from outside, then again it will intersect another line. Again, this is not a proof, but another way of seeing that the puzzle is at least difficult. Okay, now the puzzle is impossible only if we are restricted to draw the graph on a plane, on a two-dimensional plane. If we can draw the graph on a torus, say, then we can make the connections without the lines intersecting. In this case, that troublesome connection that we could not make on 2D plane goes actually from the back side of the torus. So let me show the connection to you. It goes from, so this is the connection. It goes down the torus hole to the other side and then proceeds on the back side of the torus and then comes back to the top side and connects to the node without intersecting any of the lines because it's on the other side of the torus. So when we talk about the planar graph, means on a 2D flat plane, not on the surface of a torus, for example. Now here are 2 challenge questions. These are not questions that you need to answer. It's just, they're just for you to think about. So 3D cube. shown here, is it planar? Okay, so this 3D cube, can I draw this graph so that lines do not intersect? Of course, this particular drawing has lines intersect, but can you redraw it by moving the nodes around and the edges around so that it becomes planar? And a more challenging question is four-dimensional cube, where it has 3 dimensions as in the other cube. The fourth dimension is represented basically by these lines that connect the outside nodes, these lines, to the inside nodes. If you want to visualize this four-dimensional cube with the fourth dimension being time, imagine a cube, the big cube, gradually shrinking to become the small cube. So that's the fourth dimension, the time dimension. Okay, so let me now try to prove to you that the main puzzle corresponding to the complete bipartite graph K sub 33 is not planar. Now in this proof, I'm going to use a very interesting result due to the mathematician Leonhard Euler, who developed the formula for planar graphs. Okay, it's a genius, very simple but genius formula that says if a graph is planar, as you see this graph that you see on this slide, it is planar because no edges intersect each other. So it is planar. For any planar graph, if you count the number of vertices and call them V, so this particular graph has 17 vertices. You can easily verify it. Count the vertices. By the way, the colors of the vertices and the edges don't matter. They're just arbitrary, so ignore them. So we just have one type of node and one type of edge that happen to be different colors because this graph comes from a source that needed those colors. So all edges are the same color, all nodes are in the same color. So this one has 17 vertices, and it has 38 edges. Again, you can count the number of lines that connect the vertices to verify that there are 38. What about the number of faces? Now, faces are basically areas in this drawing that are blank. They're surrounded by edges and nodes. So for example, let me mark some of the areas. This is one area. This is a second area. The white surface that you see there. So let me count the number of faces. That's 2. Here is 3, 4. I'm going to mark them so that I don't miss or double count. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 18, 19, 20, 21, and for the sake of this theorem formula, the outside of the graph is also a face. So there are 22 faces in this graph. Oops, 23. I missed one. Let me see if I can find which one I missed. I don't see any. We are just miscounted. Okay, let's accept this count because I verified this before. There are 23 faces. And then Euler said that if this graph is planar, then the parameters V, vertices, E, edges, and F, faces, are related by this formula. V minus E plus F is equal to 2. So it's easy to verify it for this particular graph. V is 17 minus E minus 38. That's negative 21 plus 23. That's 2. It's amazing. Any planar graph should satisfy this equation. In other words, if a graph does not satisfy this equation, then it cannot be planar. So here's the first question you need to answer. See if you can provide a proof of Euler's formula V minus E plus F is equal to 2. And it's okay to use internet sources. In fact, there are many different proofs for this formula. So any one of them would do. So Euler's formula actually tells us that K33 isn't planar. Why? This graph has 6 vertices. V is equal to 6. It has 9 edges because every one of the 3 white nodes is connected to every one of the 3 black nodes. So the number of edges is 9. From Euler's formula, the number of faces should be 5. Okay, so if I can draw this graph as a planar graph, if it were possible to draw it, the drawing should have 5 faces. I'm going to show that it's impossible for the drawing to have 5 faces. Why? Now, in a bipartite graph, let me go back to the previous slide. You see faces in this graph have different number of edges surrounding them. So you have some faces with 3 edges, some with 4. Okay, there's one with 5 and so on. So the number of edges can be even or odd. It can be 3, for example, it can be 4. However, in a bipartite graph, a face must have an even number of edges because of the way the graph is connected. So for example, in this drawing, this is a face. If a face has only 3 edges, that means I have to have a connection between 2 white dots or 2 black dots, but that's not allowed. Okay, the edges go only from white dots to black dots. Not between white dots, not between black dots. Okay, so a face has a minimum of 4 edges. It cannot have 3 edges. Okay, so if we have 5 faces, 5 times 4 is 20 edges. So the 5 faces will be surrounded by 20 edges. However, each edge surrounds 2 faces. Okay, so again, going back to the previous slide, you see that, for example, this edge that I'm highlighting, this edge, is common between 2 faces. Okay, so when I multiply 5 by 4, I'm double counting the edges, so the number of edges must be 10. Okay, but we don't have 10 edges here. We have only 9 edges. So that's a contradiction that shows that this graph cannot be drawn to be planar. It's not planar. So one of the implications of this puzzle not being solvable is that any graph that contains that graph as a subgraph cannot be planar. So for example, in this graph, notice that this subgraph of 6 nodes is K33. Okay? There are 3 nodes. There are 3 nodes here. There are 3 nodes on the other side. And each node on one side is connected to every node on the other side. So if K33 is not planar, any bigger graph that contains K33 as a subgraph is therefore not planar either. Cannot be drawn as a planar graph. So why are we even interested in planar graphs? Well, when we have a graph to draw, it's nice to have it as a planar graph. So for example, this is the course structure for actually required courses in computer engineering program a few years ago. It's not up to date. So you try to draw diagrams such as this one so that edges do not intersect because they become clearer and easier to understand if they are planar. Unfortunately, this one we could not draw as a planar graph. And you see that there are several intersections of edges on the graph. Okay, here's one intersection. Here are a couple. Here's one more. Okay, so there are quite a few. Here's another one. Now the question is this graph planar? And I just happened not to work hard enough to draw it the way it's shown here. For example, you may argue, what if I move this CS40 node from where it is, to this area? Move it here. So what happens? If I move it here, then the connection from MAT3C to CS40 can go here without intersecting anything. Okay, so I removed one intersection by moving that. On the other hand, because CS10 must also be connected to CS40, this makes the situation worse because connecting CS10 will create 2 intersections. Okay, so it may be possible occasionally by moving things around to make a graph planar, or at least contain fewer intersections so that it's cleaner and easier to understand. In the case of this graph, I'm pretty sure you can't do it. So it's not planar. Of course, here I also try to not only try to avoid intersections, but try to draw courses in the order they normally occur in the curriculum. So for example, Math 3A is in the first quarter, Math 3B is in the second quarter, and so on. So the location of the node is sort of indicative of when students take it. Okay, so this is basically why planar graphs are important and interesting. In computer engineering, we are interested in planar graphs because we try to wire things together. So imagine that these are points on a chip, in an IC chip, or on a printed circuit board, and we want to connect them. Typically, these nodes are connected by what we call rectilinear paths. Means paths that consist of horizontal and vertical line segments. So this is the 2 utilities and 4 houses puzzle, but I'm restricted to draw rectilinear paths. Okay, so here are rectilinear paths connecting one utility to the 4 houses. Here's a rectilinear path for the second utility, the red one, to the first house, to the second house, to the third house, to the fourth one, and then to the third. So here I managed to solve that puzzle with 2 utilities and 4 houses, K24, so to speak, using rectilinear paths. And these are more desirable for wires on chips or on printed circuit boards. Okay, there's a challenge question here. Again, this is not, you're not required to answer this one. It's not one of the 4 questions, Q1 through Q4. Here is Q2, question 2. Argue for or against the claim that if one can solve the houses and utilities puzzle with arbitrary paths, then there is a solution with rectilinear paths. Excuse me. Okay, so you have to answer this question with an argument, either for or against the claim that if one can solve the houses and utilities puzzle with arbitrary paths, then there's a solution with rectilinear paths. Okay, sometimes we want to connect multiple points together on a chip or on a printed circuit board. So for example, one of these points, black dots, can be a battery terminal, and the other 4 need to be connected to the battery terminal to get power. Okay, so I'm interested in connecting all these 5 points together so that the battery is connected to the other 5 points. Okay, so what you see here is called a spanning tree. Spanning tree is a tree. Okay, a tree is basically a graph with no loops, no cycles. Okay, so this is a tree that connects 5 points together using rectilinear paths. It's called a spanning tree. The length of wires that constitute this spanning tree is 25. You just count. Okay, so here let me see. Okay, so I'm counting 1, 2. So each of these grid cells is 1 unit wide and tall. 1, 2, 3, 4, 5, 6, 7. That's the top one. And then count all the other ones. They add up to 25. So I'm now interested to see whether I can make a spanning tree that uses less wire. Okay, the total length of wires is less than 25. So if the wires cost me money to make, I want to make the wires as short as possible. Of course, short wires also are faster in electronics. Okay, so is there a shorter, a smaller spanning tree? And the answer here is yes. Basically, I remove that wire that is of length 8 and instead insert this wire, the dash line, which is of length 7. All the 5 points are still connected to each other, but the length was reduced from 25 to 24. Okay? Of course, if I want to connect those points together, there is this algorithm called the greedy algorithm that leads to a minimal spanning tree. The algorithm goes like this. Begin by connecting the closest pair of nodes. So just basically find the distance between these nodes, each pair of nodes, rectilinear distance, and you notice that these two nodes of distance 5 are closest. Of course, these two nodes here, these two, are also separated by a distance of 5, but I choose one. Doesn't matter which one. Okay, now I try to connect this partially formed spanning tree to one of the other nodes that is closest. So that's the one. Now I have a partially formed spanning tree that has 3 nodes. Which node is closest to this partially formed tree? It is that node. It is distance 6. So I connect it. And finally, I connect the last node there to the closest node. Oops. And this gives me a spanning tree of length 23. So in the case of this problem, forming the smallest, shortest spanning tree, there's this very simple algorithm. It's called the greedy algorithm. In each step, we connect the node that is closest to the partially formed spanning tree. And that gives us, provably, the smallest spanning tree. Okay, so that's the smallest spanning tree on the left that I formed on the previous slide. On the right, you see a different way of connecting those 5 points that requires less wire. But in order to use this, you should be allowed to connect a node not to other nodes, but to wires. So for example, this node over here is not connected to another node, but it's connected through this line to this vertical wire. Okay, so if my problem is just establishing electrical connections between them, that's just as good. I don't really have to connect nodes to nodes. I can connect nodes to wires that are already there. Now this is known as a Steiner tree. A Steiner tree is a way of connecting nodes, a set of nodes, to each other so that we are allowed to connect a node to a line. We are not restricted to connect nodes only to nodes. So effectively what happens here is like we insert 2 dummy nodes or virtual nodes, and then we form the spanning tree of this network. Okay, so this is known as Steiner tree. Here's the third question for you to answer. In the Steiner tree above, shown on this slide, is the Steiner tree above the best for connecting the 5 nodes? In other words, can you construct another Steiner tree that has total length less than 20. If you can't, state why you can't. Okay, so you either answer this is the best and then present your reasoning, or no, this is not the best, or then present a better alternative. So placement and routing, that was the title of this lecture, is basically the problem we face in building electronic circuits. So suppose we have chips, as shown here, with only 6 pins. Okay, modern electronic integrated circuit chips have quite a few more pins, sometimes 10, sometimes hundreds. But let's keep the problem simple. So we have chips with 6 pins, numbered 1 through 6. 1, 2, 3, 4, 5, 6. And suppose we have 3 chips. Sorry, not 3 chips. We have 6 components, A, B, C, D, E, F. Each of them with 6 pins or 6 terminals to be connected. And the desired connections are given in this list, which is known as a net list. Okay, A1 means pin 1 of chip A should be connected to E2, pin 2 of chip E. Pin 3 of chip A, the second line, should be connected to pin 6 of chip C, and so on. So I need to place these chips on my IC board. So I've chosen this placement, ACE on top, FBD on the bottom. I could have placed them differently. But this placement is important if I'm going to be able to make the desired connections. So here are some of the connections. A1 to E2. Here is A3 to C6 on the second line of the net list. Here is A5 to F1, the third line of the net list. And then I can continue. And luckily, or actually by virtue of the good placement of the chips, I can make all the connections without intersecting each other. So this means if I have a printed circuit board, I can print these wires on the surface of the printed circuit board. And those wires, because they do not intersect, will not short circuit with each other. Okay, if I have just one surface to put all the wires on, the wires cannot cross because then there will be short circuit. Here is an actual practical example of placement and routing. It's a big problem, many components, many connections. If I place the components randomly, the connections that I need to make are shown on the left. If I place the connections judiciously, by thinking about it and using algorithms, the connections between them are much sparser, fewer connections. Going back to this example, okay, if I move A from its current location to, say, to the lower left and put D where A is, there's no guarantee that those connections can still be made, okay? So placement and routing means algorithms. We have algorithms, procedures for finding good placements of components, and then after finding good placements to make the required connections between them. Okay, I'm going to skip this. The same problem exists if you use just wires. Okay, so here is an electronic system that is built. There are chips. And instead of using a printed circuit board, we use just wires. Okay, this is sometimes done when you make prototypes before you finalize your design and make sure it works. Before committing to a printed circuit board, you do wire wrapping. Okay, so you see there's a fairly complex wiring pattern that may improve if I shift the components around and put them in the best possible positions. Okay, this is an example of a single layer printed circuit board. And you see again, wires connect different points. The wires do not intersect. And these holes on the PC board are locations typically where chips would go. So let me highlight these for you. So one chip could go here. So you see there are 2 rows or 2 columns. Point. So the chip is actually placed there with the pins going inside these holes that you see. This may be another location for another chip. So this PC board has all the wires that we require, and then the chips will simply fall into place. And all the connections between them are already there on the PC board. Okay, another example of wiring. This is the backside of a set of cabinets holding computers, servers, and then you see cables go haphazardly between the various cabinets. This is a cleaner way to do the wiring and cabling using rectilinear paths that makes maintenance much less of a headache because you can see clearly what is connected to what. Okay, another PC board. Now, in modern electronic circuits, the connections are too complicated. This is a fairly old electronic circuit. All the connections needed between the components, these light gray lines, are on the PC board, and none of them intersect with each other. But in modern electronic circuits, we have many more components, many more wires. And it's very unlikely that we can wire all the components using a planar graph, so to speak, using wires that do not intersect. So in these cases, we have multiple layers of wiring. So in this example, we have a printed circuit board with 4 layers. So the wirings are done on the 4 layers. So for example, 2 layers are designated as signal layers. So you see here, the top layer is the signal layer, the bottom layer is the signal layer. The other 2 are power and ground because power and ground must be connected to almost every component. And then the signal layers are used in the following way. Let's say horizontal wires go on this layer. Vertical wires go on the bottom layer. And then the 2 layers are connected through a via. A via is basically a hole that you drill in these layers and put metal in it so that this wire on top is connected to this wire at the bottom. And because one layer has only horizontal wires and the other layer has only vertical wires, these wires are guaranteed not to intersect. So this is a way around the situation where wiring is just too complex to put on a single surface without intersecting. So we divide the wiring into horizontal segments and vertical segments that go on two different layers, and then through holes that are drilled, we make electrical connections between wires on those two layers. Okay, this is a real example of a two-layer wiring scheme. The red wires are on one surface. The green wires are on the back side, let's say, the other side of the surface. So this is a PC board with two surfaces, the two sides, holding. These are not really exclusively vertical and exclusively horizontal wires, but predominantly, the red ones are predominantly vertical, and the green ones are predominantly horizontal. And then here's an example of a component that will go on this printed circuit board. Here's an example of a via. This hole over here, this hole, connects the red wire on one side of the board to the green wire on the other side of the board. This is pretty much what we do when we want to build freeways that should not intersect. We don't want to have traffic lights. So we use two different layers. One freeway goes on top, the other one goes below. Now, of course, we can carry this to extreme. So here, the two freeways are built, and cars can switch from one freeway to the other without ever stopping. And this is the extreme case where freeways are stacked on top of each other in multiple layers in order to minimize interference and maximize the efficiency of switching from one freeway to another one. And we do the same thing for integrated circuit chips. So here you see a cross-section of a chip on the right. The image on the right is a cross-section of a chip with 7 layers of connection. 6 metal layers, numbered metal 1, metal 2 to metal 6, and 1 tungsten interconnect layer at the bottom. So transistors, another component, are at the bottom, are built at the bottom. So transistors are here at the bottom. And then the local connections between transistors are implemented by using tungsten. Then the metal layers, metal layer 1 connects. So if you have one component over here, okay. There's one component over here, and another component further back. So remember that this is the cross section of the chip, so it's the 3-dimensional. So there's another component further back. So this component is connected through a via to this wire. And this wire is basically perpendicular to the surface that you see here. That's why you see just the cross section of the wire. So this wire goes from here to a point further back, and then goes down from there and connects to a second component. And then there's metal. So basically you see that the metal layers as we go up become thicker and longer. This is done on purpose because if you want to connect two components that are far apart on the chip, maybe one is on one side of the chip, one is on the other side, you need a long wire. And that long wire, if you make it thin, like this layer 1 and 2, will have a high resistance. And that impacts the speed of operation. Its operation will be low speed. So in order to reduce resistance and therefore increase the speed, you make these metal layers on top that go longer distances thicker. Okay, I'm almost done, so let's go to the next slide. So in this slide, you see an actual photo micrograph of inside the chip. And this is an artist's rendering of how connections are made in multiple layers. So it's exaggerated a little bit. The vertical dimension is exaggerated to show you that wires cross over one another in the same way that freeways go over one another. And then they're connected to lower layers through these vias, the vertical connection. So for example, this via connects wires on different levels. Okay. On this slide, you see two related puzzling problems that you can think about. One is the problem of resource placement. So imagine that this graph represents a small town with lines or edges representing roads between various points in the town. So circles are basically intersections or squares, main points in the town. And the numbers on the edges are travel times. So 4 means it takes 4 minutes to drive. It takes 4 minutes to drive from this point in town to this point. It takes 2 minutes to go from that point to this point. So this town needs a fire station. Where should we put the fire station so that its maximum distance, the worst case distance to various points in town, is minimized? In other words, it's optimal position for the fire station. So let me give you an example. Suppose I put the fire station over here. Of course, the fire station does not have to be on one of these points. It can be maybe in the middle of this road. Okay, let's say I put the fire station on this node. I have to compute the shortest distance, travel time, from this point to various points in town. So for example, to go from this point to this point on top takes only 1 unit of time. So that point is well served by the fire station. Okay, on the other hand, this point here, how long does it take to get there? Well, there are different paths to get there. This path has travel time 5, 1 plus 4, but there's a shorter path, 1 plus 1 plus 1. Okay, so this is a difficult problem because there are so many options to consider. Here's the second problem, robot motion planning. or path planning. So there's a robot shown as a black dot, black circle on this diagram. And the robot has to take a rectilinear path to go from where it is to its destination, desired destination, which is so the robot is here now. It wants to travel there. It has to plan its path, compute its path. And the path has to be rectilinear, meaning it has to follow the grid lines. Okay, and the robot has non-zero dimensions, so it can't go to this grid point because the wall there will prevent it from to get to that grid point. Okay, but it can do this path, go up and go to the right. Oops, I can't go there again because that wall will block it. So I have to go up, go there, and then perhaps go down. So this is one possible path. Okay? So your last question for this lecture, which is originally scheduled for April 6th, is this. Draw a shortest rectilinear path from the black circle to the white one. So I drew one path that may or may not be the shortest. Okay? So draw a shortest rectilinear path. The robot is motivated to take a shortest path because it will conserve time, will get there faster, conserve battery power. Okay. So what is the shortest rectilinear path for getting from the black circle to the white circle? Okay, that's it. So I'll be looking forward to receiving your answers to these 4 questions by Wednesday, April 8th, 6:30 p.m. All right, take care, and I'll see you in the next lecture. Bye.